In this video, we're going to explore the development of an ultra-low power tag-based system using visible light communication for IoT applications. Hello, I'm James Farmer, and along with my colleagues Graham Faulkner and Professor Dominic O'Brien, we've developed a tag-based system consisting of a tag like this, which could be worn around the neck or kept on the person, and this will communicate with a base station typically located in the ceiling. One of the key challenges that we have with this project was the link between the tag and the base station. Typically with visible light communication you would use an LED. The problem is for such a low power tag application, LEDs require far too much power. So we had to try and come up with a new solution. This is where this material comes in. This is retroreflective sheeting, and you might recognize it as it's used on road signs. We have a piece of this on the tag, and effectively it reflects light from the base station back to the receiver on the base station. We then employ a liquid crystal shutter, and by applying a voltage to the shutter we can change the contrast which the base station receiver sees. Effectively, by then running a communication signal through this shutter, we can modulate the beam going back to the receiver. Here you can see the base station in operation. Because of the modulation scheme used for communication, the link can be operated at ambient light levels up to at least 500 lux. The transmitter consists of an LED ring on the front board. A thin isolator minimizes stray light entering the receiver, which sits centered and behind the LED ring and captures the returning light from the tag. The base station is powered with a custom solution using power over Ethernet. Along with a Raspberry Pi 4, which serves as a processing unit for the received and transmitted data, the base station could provide simple connectivity to a network. Next, we'll examine the tag in closer detail. The tag is constructed of three main sections: a solar panel, the liquid crystal shutter, and the printed circuit board for electronics. Firstly, we can see the tag power source, a coin cell battery which gets recharged by the solar panel. The tag was designed to use considerably less power than a typical 3mm LED, and so should not need any additional charging. Here is the retroreflective material, which reflects light back to the base station. This box highlights the receiver circuit. When the base station sends a signal to the tag, it gets detected here. In our tests, the circuit could receive visible light communication with light levels between 10 and 1000 lux. This is the controller, which processes incoming communication and sends signals to the liquid crystal shutter to be transmitted back to the base station. This is the ambient light sensor, and it detects the amount of light hitting the tag. If the tag is put into a dark pocket, it will send the tag to sleep and conserve the battery, only waking it again when the light levels are sufficient for communication. We have also included a low power buzzer which could act as an acoustic warning in various applications. The layer above the electronics holds the liquid crystal shutter sandwiched between two polarizers, and these are adjusted to optimize the contrast ratio of the signal returning to the base station. Finally, on the back of the tag is a small e-ink display showing the various modes of operation and information for the user. In the following clip, you will see the link set up over 2 meters. The link has an illuminance of 80 lux at the tag, with ambient room light at 500 lux. The image in the top right-hand corner shows the communication signal which was programmed onto the tag's controller to be transmitted to the liquid crystal shutter. The data rate of the signal was set at 100 bits per second with a half-second delay between packets. The bottom right image shows this signal as it's received at the base station. This signal can then be reconstructed into the original seen above. Firstly, the beam is covered to demonstrate that a line of sight link has been established. The tag is then moved around the field of view of the base station to show that the link can be maintained. Potential use cases for this system could include keyless access, working along with our colleagues at LiFi, but also investigating positioning or granting access to equipment or areas within an industrial environment. Future work into this technology could look into commercialization, but also things such as a touchscreen e-ink display for providing a user interface on the tag and also reducing the form factor. We hope that you've enjoyed this video and thank you for watching. If you'd like to know more about the ELIoT project, please consider visiting our project or LinkedIn pages via the QR codes provided.